We have already discussed few examples on how to evaluate a time constant as well as the DC gain from three different test signals. Now let's take a look on a few examples on how to do that step by step. Let's consider a thermometer. Thermometer basically is a first order system. It can be any kind of thermometer. You can consider a mercury type thermometer, right? And then this thermometer, apparently it needs 1 minute to get to the 98% of the response. And thermometer is a first order system. We are going to identify the time constant of this thermometer. How to do that? How do you measure a temperature using a thermometer? So basically, how you measure it, you just put your thermometer on the entity, on the matter that you want to measure its temperature, right? And assuming that during the measurement, the temperature is constant, so basically you are giving a step input to the thermometer. So to this first order system, we give a step input. The step response of a first order system looks like this, right? This is from one of the slides when we discussed previously. So how to identify the time constant of this thermometer? It says that the thermometer requires 1 minute to get to 98% of the response. So 98% of the steady state value, it's somewhere here, 98.2, 98, let's consider it the same. So it needs 1 minute to get to 98% of the steady state response. And from this diagram, you know that 1 minute is equal to 60 seconds. That means your T, your time constant, is 0.25 minute or 15 seconds. Just that simple. If you want to have a more analytic solution for this, you can refer to the response of the unit step input here, and then you can evaluate the time constant using that equation. So the response is like this. When the response is equal to 0.98 of the steady state value, you can find the T accordingly. Of course, this is just a simple approximation. The height at 40 actually is not exactly 98. So if you want to have a precise result, precise time constant, you need to use this equation. So from here you can get the time constant equal to 0.256 minute. So this is the time constant of our thermometer. Now let's take another example or another step in evaluating this thermometer. To the same thermometer, the thermometer that we just discussed in the previous slide, to the same thermometer. Now we put this thermometer on a bath, where on this bath the temperature is changing linearly at the rate of 10 degrees per minute. And then we are asked to identify what is the error value when the steady state condition is reached. So basically, if you are measuring a temperature that is changing linearly, basically what we are doing, we are giving a RAM input to this thermometer. But the RAM input in our case here is not a unit RAM. The RAM input is 10 times of unit RAMs. The rate is 10 degrees per minute. So the slope is not 1, it's not a unit RAM, but the slope is 10 in this case. So how to evaluate it? Let's consider a case first when the input is unit RAM, when the slope is 1. When the slope is 1, like in this case, this is the response of a unit RAM response, which means the slope is equal to 1. If you have this case, if the input is a unit RAM, the steady state error is equal to the time constant, right? we have already identified before that the time constant is equal to 0.256 minute in the previous slides. That means the error when we give a unit RAM, the error will be equal to the time constant, will also be equal to 0.256 minute if we give a unit RAM. But what is asked by this question is the error when we give 10 times of unit RAM. So how to evaluate it? The error when the input is 10 times of the unit RAM will be just simply 10 times of the error when the input is unit RAM. So the error will be just simply 10 times 0.256. So it will be equal to 2.56. Okay, so these are the two examples on a first order system. I will give you a few more slides here to give an illustration on the behavior of a linear system. Actually, the slides that I want to discuss, it's not in particular for first order system. This also applies to any orders, either second order, third order, or any higher order system. I just want to discuss this property because we might need this in the next analysis of a higher order system. What do I want to discuss about this property? There is a unique property of a linear system, which says the response to the derivative of input signal will be equal to the first derivative of the response of the original signal. What I want to say here. So I have a system, and then with a particular transfer function, and then I give an input to the system. Let's call the input is R, and the system will give a response of C. Apparently, if I give to the same system, I give another input, where the second input here is equal to the first derivative of the first input. So S in Laplace domain, it corresponds to first derivative in time domain. The response apparently is equal to the first derivative of the first output. So let's take an example of this. I have a first order system where the unit step response looks like this. The input is a unit ramp, and the response, the unit ramp response, looks like this. Now, if to the same first order system I give a step input, the response is like this. Now let's compare these two inputs. The first one is ramp. Ramp signal is equal to t, function of t where the slope is equal to 1, and the unit step signal is equal to 1. It's constant of 1 all over the time. What do you see from these two inputs? You can see that the step signal basically is the first derivative of the ramp signal. So again, step is the first derivative of the ramp signal. If I give these two signals to the same first order system, this will be the response of a unit ramp, this will be the response of a unit step. If you look carefully, if you compare these two responses, the unit step response apparently is also the first derivative of the unit ramp response. You see the pattern, don't you? UT, step input, is the first derivative of the ramp input. And apparently, the unit step response is also the first derivative of a unit ramp response. And then intuitively also, if you look at the unit impulse input, basically this is the first derivative of the unit step. Mathematically, impulse is the first derivative of step. Same thing then, the unit impulse response, this one, will also be the first derivative of the unit step response. You can check it by yourself. You can show that the unit impulse response is also the first derivative of unit step response. Okay, this slide to summarize what we have already discussed in the first order system. So in general, then first order system, we can always write it into this form of a transfer function that contains two parameters, DC gain K and time constant T. Let's consider again the step response. We have already derived this step response before. You can refer back to the discussion on a step response of a first order system before. So the step response typically looks like this. The larger the time constant, the slower the response. The smaller the time constant, the faster the response. If you have a small time constant, the pole of the system will be more to the left, right? Because the pole of first order system is inversely proportional to the time constant. So the smaller the time constant, the more the pole will be located on the S-plane to the left. So more to the left. So the smaller the time constant, the more the location to the left, the faster the response will be. So this to conclude what is in the first order system. Aspects that I want to discuss with you about the first order system. Well, this is more related to the control problems, the part that we are not going to cover in this discussion. Sometimes you might have unstable first order system. That will happen if your time constant is negative. If your time constant is negative, then your pole, which is equal to -1/t, will be equal to positive. So you will have pole in the right hand plane. Your system is unstable. A thing that you have to do after you learn about the control design is you need to design a controller to move the pole from a right hand plane to left hand plane. To change, you need to design a controller that is capable of switching your time constant from negative to positive to make your system stable. You might have another case where you have first order system. Your time constant is positive, so your system is stable, you like it, it looks okay, but apparently your time constant is too large. If you have large time constant, what does it mean? Your response is too slow. You don't like a system that is responding too slow. So in that case, you want to improve the performance of the system. After you learn about a control design, later on you will be able to design a controller that will make your time constant of your first order system becoming smaller. The smaller the time constant, the faster the response. So you can improve the response speed of your system. Just for your reference, for those of you who are having a curiosity on how to evaluate a dynamic system in MATLAB, in this slide, I shared you a MATLAB code to evaluate a first order step response. So the first part that I indicated in green here is to define two different systems with two different time constants. So in this case, sys1 is a system where the transfer function is equal to 1 over 0.25s plus 1, and for sys2 is a system where the transfer function is equal to this. This part will ask the MATLAB to plot the step response of these two systems. So you will get the step response of these two systems by running these two commands. And the last part that I indicated in blue here basically is nothing more than just putting a label, putting a legend on your plot. So just to make your plot nicer. Okay, you can try it by yourself to run this MATLAB code. Then you can have an idea on how to evaluate a response of a first order system.